Hi, everyone. I'm Jacopo. Today, I'll walk you through a major upgrade on how we execute trades on-chain, Fair Combinatorial Batch Auctions. This is actually more than a new mechanism. It's about embedding fairness and scalability right into DeFi core. OK, here's what we will cover. First of all, we will see why execution in DeFi still needs work. After that, we will see what cow protocol and intent-based trading are and why auctions are core for fair execution. After that, we'll look at the limits of traditional batch auctions and how fair combinatorial batch auctions actually solve them. And finally, we will see what this unlocks for the future of traders, solvers, and DeFi in general. So let's say that, first of all, if we look at the big picture, execution in DeFi is kind of messy, right? DeFi is maturing. We have more trades. We have more chains, faster chains. We have more complex needs. But under the hood, as I said, execution still has some flaws. We have MEV that is extracted at user's expense. We have liquidity that is siloed. And the way trades settle can be, let's say, less than fair, right? As DeFi scales, we need to actually embed fairness, efficiency, and throughput right into the infrastructure, right? It has to be core to our infrastructure and not just afterthoughts. So what is cow protocol? Well, cow protocol is an intent-based DEX aggregator. What it means is that users tell us what they want to do or what they want to achieve. For example, I don't know, swapping ETH for USDC. But they don't tell us how they want to achieve that, right? They don't specify an execution path, right? What happens next, normally, is that solvers compete to fulfill that intent, right? And they try to, actually, they do shoulder all the complexity of it, right? So they take care of routing, MEV risks, slippage, gas, right? And this basically means that they provide a trading experience that is fair, that is secure because it's MEV protected, as I said, that is optimized because it gives surplus back to traders. We have a uniform clearing price, and we have the possibility of having peer-to-peer matching, right? That basically is what we call a coincidence of wants. That's, by the way, our name, cow, right? At the heart of this, there is the auction logic, and we will talk about the auction logic in a bit. So let's first speak about intent, right? And intent-based trading. I would say intent-based trading is about abstraction. Instead of users micromanaging swaps, what they do is they tell us, OK, I want to swap 100 USDC for a certain amount of ETH, right? So they basically specify a buy token, a sell token, the amount they want to buy or sell, and a slippage threshold, basically, right? What happens next, as I was mentioning, is solvers pick up this intent, and they find the best way to fulfill this intent, so the best execution, and providing the traders, let's say, the best possible outcome. Of course, this unlocks composability and modularity, right? Intents can be matched against DEXs, against chains and bridges, and even against asset types, basically paving the way for programmable finance. Who are these solvers that we have been talking about? Well, solvers are basically bots, right, that are scanning the ecosystem to find the best way to actually execute a bid and fulfill an intent. As I said, they shoulder that complexity, including the execution logic, and they have one goal, which is normally maximizing surplus for users. Why? Because if they do so, they have higher chances of winning an auction, and if they win an auction, they get rewards. It's basically a competitive game with high alignment. So what are these auctions? Well, it's basically, we are now talking of how these intents get executed, right? So or if you want, how do we determine which solver gets the right to execute a certain intent? And that's when auctions enter the stage, right? In the end, auctions are the core mechanism that Cow Protocol uses to ensure that users are protected and get a good deal. Moreover, instead of executing trades one by one, we normally batch them and solve them collectively. This is what a batch auction is, basically, right? And this normally allows for matching and price improvements that would be otherwise kind of impossible with traditional DEXs. Solver bids on one batch, and the best one basically wins. Yeah, so why going through all this trouble with auctions? Well, because auctions allow to find the best execution path and price for a given intent. They have MEV protection, and they ensure fairer execution, right? They are basically and simply more fair than first come, first served or AMM models, right? However, Cow Protocol original design had some limits, which were like, it was efficient, but only for a single winner per batch, as I said, right? So that led to underused capacity, missed opportunities, and sometimes also like some fairness challenges, right? Let's unpack these limits a bit more. So first of all, we had a single winning solution, right? Only one solver could win. This meant that sometimes good opportunities and good outcomes were left behind. On top of that, surplus was somehow skewed, right? Certain trades benefited more than others. And above all, we had to run a kind of complex ex-post fairness check or fairness test check that is called EBBO after every auction, right? It worked, but it wasn't scalable or transparent enough. So let's look at how, let's say, an old auction works, let's say, right? And basically, we have a batch of orders. We have Emily that wants to swap ETH for USDC. We have Edith that wants to go the other way around and swap USDC for ETH. We have Chow that wants to swap 1 inch for Cow. And we have René that wants to swap ETH for Aave. I really hope you like rhymes, because it took a while to find the right names that were rhyming with those tokens. So, yeah. So in a traditional auction, what happens is we have solver A that bids on the first 3 orders, right, on Emily, Edith, and Chow, and wins. However, we had solver B that had a better execution for order 3, for Chow's intent. And we have solver C that had also a B for René's intent, right? But both solver B and solver C got ignored. Why? Because we have a single winner constraint, we said, right? So only one solver can win. So you can see the problems here, right? We have some surplus that is missing because, of course, solver B had a better execution. We have a lower total throughput because some orders didn't get executed. And we have also to perform now a post-facto fairness check, in particular for order 3, the one where we had a better execution and a better outcome that was not considered. So I think it's pretty clear why we needed a change, right? Cow Protocol is expanding across chains, as you probably heard in the last few days, and is managing more and more trading intents. So there is the need for, of course, more throughput, more fairness in how we distribute surplus, and more decentralization. The single winner constraint was kind of held in the protocol back, right? It was time for something better, something fairer by design. And that's why Cow Protocol built Fair Combinatorial Batch Auctions. Let's see how Fair Combinatorial Batch Auction work. Sometimes we call them FCBAs, but yeah, I'll try to say the long name now. Yeah, so in a Fair Combinatorial Batch Auction, solvers bid and submit multiple bids, right, and on individual or batch trades. Then these bids are basically compared, like the outcome of these bids is compared against a fairness benchmark, what we call a reference outcome, right? And only if a bid, right, an all traded, let's say a batched bid, provides a better outcome compared to all individual trades in that batch, it is eligible to win. Then, from the surviving bids, right? Multiple solvers can win, actually multiple solvers can win the same auction, as long as they meet this fairness criteria. Before I move on, let me pause for a second and explain a bit better how this reference outcome works. So the reference outcome is basically, let's say, a benchmark constructed on the best bids that we can have on individual token pairs and direction. So let's say no batching or combining happened. What would be the best execution on each individual trade on its own, right? Once we have that, what we do is when a solver submits a new batched bid, let's say the one where we had order 1, 2, and 3 combined earlier, like in the example I showed you earlier, this bid is only accepted if the reference outcome across all token pairs in that bid is actually beating, basically, the outcome that you will have in each individual trade alone, right? So this way, batching can never make a trade worse off than it would have been if it was just executed alone. Maybe to explain this a bit better, I can jump back to the previous example, right? So what happens here is we had solver A that made a bid on order 1, 2, and 3, and solver B had a better execution for order 3, so Chow, that was the one that, let's say, manifested that intent for order 3, got a disadvantage here, right? With fair combinatorial batch auction, this couldn't have been possible because solver A with his bid would probably been filtered out in the sense that he wouldn't have a best outcome for all orders included in that batch. And we can actually see what happens in practice here, right? So we still have solver, it's the same batch. So we still have solver A bidding on orders 1, 2, and 3, Emily, Edith, and Chow, but it gets disqualified for the reason I said earlier. There is a better execution for Chow's trade, right? Solver A can still win the coincidence of wants between Emily and Edith. You can see there are the same token pairs in different directions, so it's a coincidence of wants. But this time, solver B actually wins Chow's order, right, order 3. And solver C wins René order, right? So you can see the advantage that we have here with FCBA. We have a higher total surplus, of course, because we have the best outcome possible. We have more trades that are executed, so we have a higher throughput. And we don't need any post-facto fairness check. This is just a clear multi-solver win. So you can say basically that in FCBA, fairness is not just a patch, is the design, right? It's encoded in the design. Solvers are rewarded based on how better outcome they provide compared to the baseline. Trades in the same direction, right, token direction, get the same price. Like, so we have a uniform price there. And hook logic and fees and gas costs are accounted for. What about the EBBO, that fairness check that I was mentioning earlier? Well, that becomes obsolete in the sense that fairness now is checked before execution and not after, right? And this is in theory, by the way. In tests, we have already noticed that like fair combinatorial batch auctions are bringing 33% more order throughput. That means that cow swap is faster now. That's especially true, by the way, in volatile times, right, when there is high congestion. Imagine this as a highway with high traffic, and basically you are suddenly adding another lane. Of course, this way you can actually move from point A to B faster. On top of that, we have 25% more solver rewards. So this is kind of interesting, right? Because in the end, what we are providing is a surplus distribution that is more equitable. We have stronger incentives for solvers that increases both competition and quality. And we are laying the foundation for a unified order book across all chains, which is quite important. So basically, fair combinatorial batch auctions are breaking the winner-takes-all mold, right, if you want to put it this way. They are encoding scalability and fairness right into the mechanism. They are just not more efficient, they are more just. Yeah, I'm a marketing guy, so I had to make this one, sorry. Yeah. Anyway, this is kind of crucial as DeFi grows, right? Because users won't just want like fast and cheap. We can still achieve, but they will start to demand also fair and transparent. So what does this mean on the ground? Well, it means that for traders, we have better prices and consistent execution and outcomes, right? For solvers, we have more ways to win and smarter bidding strategies. And for protocols, we have a sustainable way to scale without compromising on fairness or decentralization. And we are only scratching the surface here, actually, right? Because Fair Combinatorial Batch Auctions enable future-ready features like cross-chain auctions, like multi-user trade optimization, or modular auction logic, right? These are actually the building blocks of the next-generation DeFi stack, which is composable, which is intent-based, and which is like fair. Okay, so what's Cow Protocol long-term vision? Well, to make execution in DeFi not just performant, but principled. Cow Protocol wants to be intent-aware, wants to be fair by default. It wants to be modular and scalable, right? Fair combinatorial batch auctions aren't just a feature, are, let's say, the way Cow Protocol sees the future of DeFi for the next decade, I would say. To wrap it up, let's say that DeFi promised open markets, right? Let's say that openness is not enough. We need to somehow embed fairness right into the infrastructure, right? With Fair Combinatorial Batch Auctions, we are actually embedding fairness and efficiency where it matters the most, which is the auction itself. We are building a future where rules don't just allow for good outcomes, but they guarantee them. Thank you. By the way, I've been told that, and I know that Cow is hiring. We are hiring for different roles, right? In particular, we are hiring for Rust engineers. So if you are a Rust engineer or you know Rust engineers, this is a very good time to raise your hands or speak with me, or we have our HR lead, Maria, which is great, by the way, so you can chat with her. Even if you're not a Rust engineer, if you are good talent, this is a good time to talk with our HR. Thank you, everybody.